At 10 o'clock on an April morning, 51 construction workers stood 166 feet above the ground on a ring of scaffolding. Beneath their boots was the wall of a cooling tower. The concrete supporting almost everything around them had been poured the day before. Minutes later, the upper edge of that tower began to peel inward. The scaffolding, forms, cranes, equipment, and every worker on the platform fell into the hollow center. The warning at Willow Island was not hidden in a secret memo. It was built into the structure itself. The tower was being asked to carry the machinery that was building it before its newest concrete was strong enough to carry the load. In 1978, the Pleasance Power Station was expanding beside the Ohio River in West Virginia. 2 huge natural draft cooling towers were part of the project. One had already been completed. Its hyperbolic shell rose 430 feet above the site. Beside it, a second tower was climbing toward the same height. The shape looked massive, but the concrete shell was relatively thin. It curved inward as it rose, and both its diameter and wall thickness changed with height. Building it required a specialized lift-form system that moved upward with the tower. There was no separate tower crane or independent scaffold rising from the ground. The forms, working platforms, and material handling equipment were carried by the concrete shell that had already been built. At 96 points around the circumference, paired beams were bolted to the inside and outside faces of the wall. Jacking frames traveled along those beams. 4 levels of scaffold hung from the frames. Workers placed reinforcing steel, adjusted forms, patched the finished surface, and received buckets of concrete at the top platform. When one 5-foot band of wall was complete, the system leapfrogged upward. Lower beam sections were unbolted, moved above the others, and attached to newer concrete. The forms were raised. Then the next band was poured. For much of the tower, the schedule called for one 5-foot lift every day. That rhythm created an unavoidable engineering question: how strong was yesterday's concrete when today's construction load arrived? By April 27, the second tower had reached lift 28. It stood 166 feet high. Lift 28 had been poured the previous day. The forms and the entire moving work system had already been raised into position for lift 29. 6 gantry cranes, called catheads, were spaced around the rim. They lifted reinforcing steel and buckets of concrete from the ground to the upper platform. Each cathead, its cables, the suspended scaffolding, the forms, the workers, and the material being moved transferred force into the young shell below. The tower was not carrying only its own weight. Its newest concrete was carrying the active construction site that surrounded it. Just after 10 in the morning, concrete placement for lift 29 began. According to the investigation, roughly 1 cubic yard had been placed. The third bucket was being raised toward the platform near cathead number 4. Then the hoist cable went slack. The cathead began to tilt inward. Witnesses saw lift 28 rupture in that region. The failure spread around the circumference, first in one direction and then the other, as the top band of the shell unwrapped and fell inward. The 4-level scaffold was anchored to that same section. Once the shell failed, there was no independent support left beneath it. All 51 workers on the scaffold were killed. The scale of the loss made Willow Island one of the deadliest construction disasters in United States history. But the first explanations had to be tested carefully. Did a cable snap? Did the concrete bucket strike the gantry? Did an anchor bolt fail first? Or did the scaffolding itself give way? The Occupational Safety and Health Administration began investigating that day. 2 days later, a team from the National Bureau of Standards joined the work. Investigators examined the site, tested concrete and hardware, reconstructed the hoisting system, interviewed workers, and built computer models of the thin concrete shell. Their evidence changed the sequence of cause and effect. The major components of the hoisting, formwork, and scaffolding systems had not failed before the shell. The bucket had not struck cathead number 4. Damage to bolts and equipment was largely consistent with forces released during the collapse, not with a single component starting it. The most probable initiating failure was the concrete of lift 28 itself. The investigation found that construction loads were imposed before that concrete had gained adequate strength. Near cathead number 4, calculated forces equaled or exceeded the young shell's capacity in compression, bending, and shear. Once a local section failed, the continuous ring could no longer redistribute the load safely. Failure propagated through the entire lift. This is what made the construction method so unforgiving. Every part of the moving system depended on the newest completed portion of the tower. The weak link did not support one machine. It supported the platform, the forms, the lifting equipment, the materials, and the people working around the rim. A later National Bureau of Standards analysis asked how much strength would have changed the outcome. Its model found that crushing failure could begin if lift 28 had a concrete strength of 1,000 pounds per square inch or less. To maintain a safety factor of 2 under the analyzed loads, the concrete would have needed to reach 4,000 pounds per square inch. The same analysis examined other details. A lower line of bolts between the exterior beams and the shell was not in place at the time of the collapse. Adding those bolts would have reduced some stresses, but the model found that the weak concrete in lift 28 still would have failed. Another change mattered more. The ground anchor for the static guide line had recently been moved closer to the center of the tower. In the case-specific follow-up analysis, keeping it at its earlier location would have reduced the construction forces enough that the failure probably would not have occurred. That does not reduce Willow Island to one misplaced anchor. The deeper failure was the absence of a safe margin between the strength the young concrete had actually developed and the combined loads the construction process placed upon it. Concrete does not become safe because a schedule says the next lift is due. Its strength depends on time, temperature, mixture, curing conditions, and verification. A process that advances every day must still stop when the structure beneath it cannot prove that it is ready. Willow Island shows how speed can turn a structure into its own test rig. Each completed lift carried the apparatus for the next one. Each successful day could make the routine feel validated. But repetition was not proof of safety. It only meant the margin had not yet been exceeded. The tower gave no dramatic warning before that morning. There was no fire and no storm. The danger was quieter: fresh concrete, accumulated construction weight, changing cable geometry, and a workflow that moved upward faster than the material gained strength. 51 workers paid for that missing margin. The lesson is not that ambitious construction systems are inherently unsafe. It is that temporary construction loads deserve the same engineering discipline as the finished structure. Strength must be measured, load paths must be understood, and work must be allowed to stop. At Willow Island, the warnings were there. They were written in the age of lift 28, in the weight hanging from it, and in the decision to build the next day on concrete poured the day before.